All right, so I'm going to do the impossible this morning, which is to tell you all about the foundational mathematics of leading up to 3D reconstruction, 3D classification, all that stuff. So I'm doing this in three parts, and this is the first part where I'm going to review complex numbers. I know a lot of you've had that in high school or whenever. Right, and the big deal in this part of the lecture is how contrast happens in the electron microscope, how defocus contrast happens, and how we can model it. So complex numbers, you probably remember them, and the reason we talk about them is that the equations are simpler, they're good for Fourier transforms, and everyone's using them for getting magnitude and phase of structure factors. So a complex number is based on the imaginary unit I, and a complex number has some mixture of an imaginary part and a real part. And you can do all the operations you would want to do with complex numbers. And the thing that I really want to emphasize, because we're going to use it a lot, is this thing called the complex exponential. So you remember what e to the x is. So e is this transcendental number, and one way of representing e to the x is this Taylor series. And a really useful approximation when x is really small is just say, well, e to the x is approximately equal to 1 plus x. And we're going to use this approximation a lot. Now, the complex exponential is defined as a cosine function, which is the real part, and a sine function, which is the imaginary part. And so if you try to plot this thing, what we're going to do is we're going to plot imaginary versus real. If you plot it in 3D, you see the thing is a helix. And the helix has a periodicity of 2 pi radians, and it's circling around it. The result is you're tracing around the unit circle repeatedly. Finally, any complex number can be represented two different ways. You can do what we just described, which is the real and imaginary parts, and you do it in this complex plane, and there's our number. But another way of representing it is to say, well, there's an angle, a phase angle theta, and a magnitude, which is this radius r. And so you can represent it either in this Cartesian way or in this sort of polar coordinate way. That's all I'm going to say about complex numbers. Any questions yet? No, you're probably all very happy or bored or something. All right, I'm going to increase the magnitude of your image on my screen so that I can see you better. Hang on. There we go. Hi, class. Okay, so now defocus contrast. So the useful contrast that we get when we image a cryo-EM specimen is phase contrast. Basically, when an electron wave passes near an atomic nucleus, it sees a positive potential, and that speeds up the electron briefly, and that shifts the phase so that the electron wave after it's passed by there is different in that it's been shifted in phase from the unscattered wave. And this is how we're going to make images, is make use of this phase shift. And the phase shift is really small. There's this interesting coefficient that says you get about 0.5 milliradian, so what's that, 1/16 of a degree of phase shift per volt angstrom of integrated potential. So what we do is we defocus the microscope in order to see our object. So as we change the amount of defocus, we get different looking representations of our original object. Um, we defocus in a way that's called underfocus, and I'll tell you why later. And at high defocus, the high resolution information is strongly delocalized. But at high defocus, the low resolution information comes through much more strongly, and it's easier to say pick particles when you have lots of signal from using a high defocus. Uh, Now, image processing can relocalize the signals no matter how much you delocalize them, but at most only about half of the theoretical contrast is preserved by defocusing. That is, in principle, if you have a fancy device called a phase plate that I'll describe in a little while, you get twice as much contrast as defocus contrast. Now I'm gonna do a test specimen here, which is just a grating with 5 angstrom periodicity. Imagine a beta sheet or something. It has about that periodicity, and as we defocus again, we see this thing where the contrast is coming and going, and also we have some delocalization of the signal from the object. And so we want to understand how it is that we get an image in the first place, and what's happening when we defocus. So electron waves, have short wavelengths. 300 kV, it's about 2 picometers, but those electrons are going really fast. And physicists would write the wave function of an electron wave is this e to the ikz. Here's our complex exponential. It just says the electron wave is represented by one of these complex exponentials where it repeats every let's say 2 picometers. Now, if we insert a phase shifting object that slightly perturbs the phase, so this is my phase shifting object, then the electrons come in as nice plane waves and they come out a little bit wiggly. Here you can see it better. Plane waves, they come out slightly wiggly. And so here's mathematically, my object is going to be a grating. It's going to be cosine. It's a cosine function with a periodicity d, which is going to be 5 angstroms. And it's going to have a very small amplitude. So this is just a small perturbation of the phase. And so right after the object, we have the wave function is e to the I, and then this phase perturbation. Okay. Now we make a very important approximation, which is called the weak phase approximation. So the perturbation is set by this number epsilon, which is really small. And then we make use of this of the approximation that I just talked about. E to the x is about equal to 1 plus x. And so we can say that this complex exponential just becomes 1 plus whatever the exponential was. This is called the weak phase approximation, and it makes everything much simpler, and it's just exploiting the fact that we don't get a lot of phase shift of electrons going through most of our objects. So these two terms in the approximation have physical meanings. So this one means is the let's say the undiffracted wave that goes straight through, and this thing that has an imaginary amplitude is the diffracted wave or diffracted waves. And in fact, for a grating, what we can say is here's the undiffracted wave, and there are 2 diffracted waves. You can kind of see them here. So here, the incident waves are coming down here, and then you see something going on where you see at a very fine, very weak angle, very small angle, you can imagine 2 different diffracted waves moving like that. And so if we now do the same trick of varying the defocus. That is, we're going to focus at different regions below the specimen, which is sitting right up here. We get varying amounts of contrast. There's a point here where there's no contrast, and then there's more contrast in the opposite direction. Now, how do we get contrast anyway? Well, what's happening is that the undiffracted wave is interfering with the diffracted waves, and the diffracted waves are moving at this small angle. It's very small because the sine of that angle is lambda over d. And so if we pick some point down here, what we're looking at as far as the intensity is, we're looking at the intensity of the undiffracted wave plus the diffracted waves that have come down from other locations on the object, and they interfere right here. So the point here is that the diffracted waves have a different path length. Okay, so the path length is longer by a small amount, which we'll call zeta. And here's a formula for it. And here's an example. So if we're using 300 keV electrons, and the grating is 5 angstroms, and if we sit here at 100 nanometers below the specimen, then the difference in path lengths is 0.8 picometers. It's about half an electron wavelength. So then if we define the phase difference between the undiffracted and the diffracted waves, that phase difference is just going to be 2 pi over lambda times this distance difference. And if we do this example, the phase difference is 0.8 pi. Okay, you like that? This is an important point. So shout out if you have a question. Okay, so the phase of the perturbation of this interference is a big deal because we're saying we have an undiffracted wave, which we say has amplitude 1. And this is our complex plane. And so we say this is it has a real value of magnitude 1. So we're right here. And now if we add to it a diffracted wave that changes in this direction, that is, it just has an amplitude of I, we're not going to change the magnitude of the result much at all. But if the perturbation is real, that is, it's not imaginary, but it's real, then when we add epsilon, 1 plus epsilon, 1 minus epsilon, we actually get a difference in the magnitude. And that's how it's going to work. We want to have a difference in the intensity of the waves coming from our phase difference. And so we can't do it if we just leave the undiffracted and diffracted waves as they are. We have to somehow get a phase shift such that the diffracted waves come out being real. Okay, so here's another part of the simulation. So this is what I showed you before, and if I really magnify this, yep, there are these little electron waves that are so tiny that we can't see. So what I'm going to do first is I'm going to unwrap this periodicity. And the way I will do it is I'm going to divide the actual wave function by the unscattered wave function. And so what that does is instead of oscillating at this incredible rate of once every 2 picometers, it doesn't oscillate at all. Okay, so here is the undiffracted wave, and it's equal to 1, a real value. And now still we see this interference going on. Now the next trick is let's get rid of the undiffracted waves so we can see what those 2 diffracted waves are doing. So here they are, and you can see I've colored them according to phase, and you can see up here, yes, they're imaginary. We see blue and yellow, uh, blue and yellow meaning these are, it has an imaginary amplitude, and here is red and green. That's what I want. It has a real amplitude, and we get interference at that point. And the interference is gives us then a variation in the intensity. Okay, is that cool? Somebody, somebody raise your hand and say that's cool. Nope. Okay. No way. Okay, so now you're not going to like this, but it turns out that everyone does under focus, which means that they're actually focusing the microscope above the specimen. So here's the level of our specimen. We've been talking about what happens below. But if we extrapolate the waves upward, we can then sort of mathematically say, well, if the specimen weren't there, but we were just looking at waves propagating in free space, we can ask, what would the waves be up above? And so we can do that mathematically, and we can do this trick where we say, okay, so suppose we do focus above the specimen. Well, we just get the nice continuation of this contrast. So uh, so here's the terminology. We usually, when we talk about the amount of defocus, when we take an image, we're always talking about focusing above the specimen. So I'm going to use delta for the amount of defocus, and z increases downward. So that's the definition of delta. We also talk about spatial frequency, which is 1 over the grading periodicity in this example. And the phase shift chi, which is the phase shift between those two waves, is proportional to the amount of defocus. And so the contrast transfer, that is how much contrast we get out of here from having a specimen phase grading here, is equal to the sine of this phase difference chi, and it's approximately this. Okay, so what we see here is that the amount of contrast varies as a sine function of the amount of defocus. But another way of looking at it is to say, let's pick one level of defocus and ask what the contrast is as a function of spatial frequency, as a function of the grading periodicity. And you know it's going to change, because as we change the grading periodicity, we're going to change the angles between those two diffracted waves, and so we're going to have a different periodicity of maxima and minima in the signal. And in fact, this is what it looks like. Here's chi. Chi varies as the spatial frequency squared. And so when we do the sine function of the spatial frequency squared, we get this accelerating sinusoidal variation. Now, we usually use defocus values on the order of a micron, maybe a bit more, maybe a bit less. And when you think about it, a micron of defocus, if we are defocusing a whole micron, a whole 10,000 angstroms above the specimen, that's a really long distance. It's, 500,000 wavelengths, because the electron wavelength is so short. And this has big ramifications. We're actually relying on the fact that in a good microscope with high coherence, electrons take exactly the same path through the column. They don't come through at different angles. And the reason that's important is that we're imaging what amounts to an interference pattern 500,000 wavelengths away from the object itself. And if electrons come through at different angles, the the all important interference pattern is going to be washed out. So that's why we spend an extra $1 million um, uh, um, to have high coherence electron sources, field emission sources. Okay, so let's talk about delocalization for a minute. So we know this angle theta, which is between the undiffracted and the diffracted waves, and we're going to defocus this distance delta above the specimen. And so we can ask, well, how far away is the relevant diffracted wave from the undiffracted wave? Well, that's just geometry, and we can work it out. And by a small angle approximation, it's just delta lambda times S. I apologize. S is now spatial frequency, starting with this slide. And so if we do an example, 3 micron defocus and 3 angstrom resolution, then the amount of delocalization is 200 angstroms. So that would say that if we really wanted to use that much defocus, we actually ought to leave a border of 200 angstroms around our object. This doesn't quite work. This is from the famous TRIP-V TRIP-V1 data set from Yifan Cheng's lab, and this is the size of the box that they use to box out their particle images. And the box looks like it's really big, but it is not quite big enough to actually contain all of the delocalized information at such a high level of defocus. Less defocus, less delocalization. Most of their images were below 3 microns. Okay, so do you like that? So this is our first sort of practical tip here, is that you can estimate how big the box needs to be around your particle image to include all of the delocalized information. Okay, so let's do some more details about the contrast transfer function. Are we okay, guys? I need a smile or a wave or something. Good, thank you. Okay, so now let's think about what happens when what happens in the microscope, because we want to know what's actually happening down here at the camera where we're taking pictures. So here's a lens. The lens focuses the undiffracted beam down to a point, and then it spreads out again. And so down here we have undiffracted beam, and here are 2 diffracted beams, and we have the same relationship of phase differences and so on down here as is happening up here at the specimen. But notice that now we have what would be the extrapolation of the wave fronts up above the specimen here, magnified down here at the camera. And so that means that when we do underfocus, we can actually be looking above the specimen, so to speak. So underfocus means that the actual focal plane, the conjugate plane for the specimen, is down below the camera, and the conjugate plane for where the camera is above the specimen. So that's what I mean by underfocus. We're looking above the specimen. Now we're going to start looking at embellishments to the contrast transfer function. So the first one is spherical aberration. And spherical aberration, it's a terrible name. It just comes from the fact that in glass lenses, if you make a glass lens out of with spherical surfaces, then at high angles, the lens focuses more strongly than at low angles. And so we can say that the spherical aberration changes the defocus, makes it smaller in a way that goes as the spatial frequency squared. So it goes as the size of the angle, size of this diffraction angle squared. So what we have to do is now what we have to include not only our regular defocus but this modified defocus delta prime, and if we go and work it out, it looks like this. So here is the original defocus term. Depends on the wavelength, depends on the amount of defocus and on the spatial frequency. And then here's a new term that depends on the spherical aberration coefficient, the wavelength, and the um, and the frequency. Doesn't depend on the defocus, but it has this really steep frequency dependence, s to the fourth. And if you go and work it out, it turns out that the coefficient that we have in our microscopes, that's around 2 millimeters, means that this term becomes important only at fairly high, well, I don't know if you call this high resolution anymore. You have to worry about it above about 4 angstrom resolution. The other thing is that now and then an electron passes really, really close to an atomic nucleus and it gets scattered through a really high angle. And if you are using an objective aperture, those electrons get lost. And so we get a little bit of negative contrast from high angle scattering. This means that we have a little bit of amplitude contrast even in the absence of any defocus. And I like to put it in my formula here. I say the amount of amplitude contrast is this small angle alpha, but other people take it outside of the CTF formula and just say, well, the CTF is all these terms, and then we do minus alpha as the amplitude contrast term. Okay, so here's the plain vanilla defocus contrast transfer function. That's what chi looks like. There's the accelerating sinusoid. And now when we add these other terms, look what happens. So here's alpha. This is the amplitude contrast term. It means that we start out with a tiny bit of contrast at 0 spatial frequency thanks to that. And then at high spatial frequency, we have the effect of the CS term that actually starts to reverse and is actually going to make the chi function start to move in the other direction. So altogether, this is then what the CTF looks like. It's non-zero. It oscillates, and then the oscillations actually switch in direction and start oscillating rapidly in the other direction. So that's what the spherical aberration does to us. And here's our 4 angstrom effective spatial frequency. So the spatial frequency in inverse angstrom. So here's the point where I would say that CS starts to take effect. And see, when we get down to 2 angstrom resolution, the CS, the spherical aberration is getting to be really important. Okay, so now why do we use under focus? Well, the reason for doing under focus is that makes the defocus part of the CTF start off going in the negative direction. And that's just what we want, because the amplitude contrast is also in the negative direction. Where there is stuff there in the specimen, the image looks dark, and where there's stuff in the specimen, the image is dark because of the amplitude contrast, and it's also because of the defocus contrast. So we have those both taking off in the same direction, and the amplitude contrast helps us in that respect. Now, the people who do material science, who at least in the old days, they didn't like to do computer processing of their images. What they would do is they would defocus the microscope just a little bit, just enough so that you had a nice spatial frequency range where the contrast was uniformly negative, it turns out. And they do that by making the chi function kind of flat. And so they pick a small amount of defocus so that you really get pretty good looking images without any computer processing of the images. And this is called Schertzer defocus. This guy Schertzer said this is a good place the um, uh, to do the focusing, but we don't like it. And the reason we don't like it is that the amount of contrast transfer at the low spatial frequencies, which are the ones that are going to allow us to actually see where our particle is, um, that amount of contrast is pretty low. Okay, uh, so that's the simple version, and just for you math jocks, I just wanted to put in the math of um, of how the interference works. So here is our um, uh, here is our wave function, undiffracted and diffracted, and quantum mechanics tells us that the intensity is the magnitude squared of the wave function, and that's going to be the real part squared and the imaginary part squared. And so if you work through all this stuff, the real part squared is this 1 plus 2 sine of chi times the original phase object plus a couple terms that are of the order of epsilon squared. And because epsilon is already a small number, epsilon is a really small number, and so we can ignore those. So we just say, okay, the intensity under the weak phase approximation is just going to look like this. We're going to ignore this one that just says that's the constant background intensity. And so the intensity is going to change with this sine chi multiplier. People also throw away the factor 2 for some reason. Well, people aren't doing really quantitative imaging anyway. And so we just say that the contrast transfer function is the change in intensity per unit change in electron phase. And it just goes as sine of chi. Okay. All right. Finally, the faceplate. So the faceplate is a really wonderful device. The idea is, we have this problem that when we're in focus, there's no interference between the diffracted and the undiffracted wave. So what you do is you insert this device that maybe doesn't shift the diffracted rays, but shifts the phase of the undiffracted wave by some amount, say 90 degrees. If we shift it by 90 degrees, then the CTF becomes a cosine function. Okay, and you'll remember cosine of 0 is 1. That is, this is going to be a CTF that starts out, instead of starting out essentially at 0, like the sine function, is starting out at 1, like a cosine function. And this gives really awesome looking images. You can see, you can really see your molecules a whole lot better than you can in defocus contrast. And so this is minus CTF plotted as a function of spatial frequency, and so this cosine CTF is perfectly flat until spherical aberration takes over and it starts to oscillate. But the point of this graph, and this is work by Rado Danev, the point of this graph is that your microscope has to be really, really carefully focused in order to make this work, because if you're off by 60 nanometers in the amount of focus, that's about as far off as you can get and still able to get something like 4 angstrom resolution. So we're actually really lucky that we can estimate the amount of defocus very precisely just from looking at a micrograph. Um, but if you take an in-focus picture with a faceplate, it turns out that it's very hard to determine what the amount of defocus was. And so this is technically a lot harder than you might imagine to acquire data this way. Okay, so we can just look at a micrograph and see what the amount of defocus is. And the way we do that is we compute what's called a power spectrum. So if you have a micrograph that has some stuff in it, and you take the power spectrum, which is the magnitude squared of the Fourier transform, what you see is this oscillating bright and dark rings. And the dark rings are the zeros of the contrast transfer function. So if we just looked along here, and if we were to plot that, that would just look like the square of the CTF. Now, in this representation, each pixel in this plane represents, in effect, the signal from a grating. So if I start looking at points displaced from the origin, as I move farther from the origin, I get finer and finer gratings. The direction I move in this plane tells me the direction in which the grating is oriented, and so this representation in this spatial frequency plane is really quite useful if we're thinking about gratings and we're thinking about spatial frequencies. And this brings us to Fourier transforms, which is going to be the next part of my lectures. So while I'm changing slides, please, somebody asked me a question.
Couple of questions. Let me walk.
Yeah, yeah.
Hi, Fred. Thanks for the great seminar this morning. I have a question that's kind of been plaguing me for a while now about sphere collaboration. So you're saying it's important for essentially any kind of reconstructions below 4 angstroms, or at least signals that are below 4 angstroms.
Yeah.
So does that mean when you're reconstructing something underneath, let's say you're aiming for like 3.5 angstroms, does that measurement of sphere collaboration in that microscope become essential? Like, do you have to be very, very accurate at that measurement? And how do you measure it?
Right. So measuring it is non-trivial, and almost you can, for all practical purposes, just rely on the value that your service engineer gave you, or the manufacturer told you what the value of CS is. So it's basically a property of the exact geometry of the magnets that form the objective lens. So I think people doing anything but the very highest resolution sub-angstrom kind of reconstruction can just use the manufacturer's value. So CS is important, but it's important just that you have to include that term in your CTF, and of course all the software knows to do that. I think you give CS, for example, when you first import images into Reliant, at least.
Yes. Okay, thanks, Fred.
Hi, I just wanted to go back to the section about defocus.
Yeah.
One thing that we know is that at at very close to focus, you get very little contrast at the lower spatial frequencies. And
Right.
looking at the equation for the CTF, I think that makes sense. You can just clearly see the graph. But
Yeah.
I'm having trouble connecting that to a more intuitive understanding of why that happens. Like, what's the physical reason for why you get such little contrast at low spatial frequencies?
Yeah. So let's see. We'll see in the next lecture. No, we'll see next hour that your typical object, macromolecule, has a whole lot more signal in the low spatial frequencies than in the high spatial frequencies. And so that means, as far as being able to see your see your macromolecule, high defocus is better. See it by eye. Now, as far as getting the really high resolution information, you can get that just fine at really low defocus. But the and I'll just go put that picture back up here. Um, yeah, okay, you got my whole screen there. But so at zero defocus, you actually do get a little bit of signal, and that's just from the residual of the spherical aberration. But anyway, does that answer your question?
So I guess I want of a more physical reason for why you get low contrast at higher spatial frequencies. Just what's happening in the microscope or to the electron rays to make that contrast not visible.
Yeah. So what's happening is this. Let's see. Low defocus means that we are picking off the interference right here, very close to the specimen, and um, uh, and that means that we have no interference until we get to pretty high spatial frequencies. That's the way to think about it. Is that helpful?
Yes, I think that does help. Then just the other thing was trying to relate this to traditional light microscopes. So on light microscopes, we try to be at focus as much as possible. So what's different with electron microscopes that we want to be at? What would be that fundamental difference between light microscopes and electron microscopes to make the focus value different?
Well, we have the same problem with light microscopes. It's just that light microscopes have nice phase contrast devices. They have phase plates and they have Nomarsky interference optics and so on. So they've solved the phase contrast problem by having the right kind of optical components. And it's just been really hard to make the right optical components for electron microscopes. So if you have just a plain bright field microscope and you're trying to look at, say, a cultured cell that's basically transparent, it's just a phase object, you won't see anything until you throw the light microscope out of focus.
Okay, thank you.
Yeah.
One more question, Fred.
Yeah.
Hi, Fred. I just got a quick question about faceplates. In practice, what are the pros and cons of using faceplates?
So the pro is, of course, you get this wonderful large amount of low frequency information. And I think the practical way to use a faceplate is to use it with defocus. If you defocus it some, then you get those wonderful rings. They're called tone rings in the power spectrum, and you can estimate very precisely what the level of focus is. So then the advantage is just that you have extra signal at really low frequencies. That means faceplate is really great for doing tomography, where you're really interested in low frequency information. Now, everyone thought that faceplates were gonna give us better results, but Rado Danev did some careful measurements and decided that at high spatial frequencies, the fact that there's a device there in the electron beam happens to be an amorphous carbon film, perturbs the high spatial frequency information and reduces the amount of signal there. So in the end, single particle people don't like faceplates. It might be interesting if you have an extremely challenging small molecule where just localizing it is important, but I think no one's using faceplates for single particle.
Okay, thank you.
Not clear. Yeah.